So another type of limit is what we call a limit at infinity, not to infinity. So a limit at infinity is, we're going to notice down below here in the problem, that this time, instead of x approaching a specific number, we want to know what happens to our outputs when x grows without bound. So we might recall in some of our earlier videos, we had sequences that grew without bound. Their limit was infinity. So we're going to use that as our input in our table and then see what happens to the outputs, just like we did with the other problems. So go ahead, grab your calculator, and we're going to put in the function, the square root of x squared plus 5. Make sure you put parentheses around the x squared plus 5, right? So your calculator kind of, whoops, gotta go back to a marker. So you'll have a square root and then x squared plus 5 in your calculator. And let's go ahead and make, excuse me, a little table here. So we've got x, square root x plus 5. And again, the sequence you create, it really doesn't matter what the numbers are, just as long as the numbers get large sort of very quickly, so that we can get a feel for x approaching infinity. So I like to use, just because it's easy, 10, 100, 1,000, and 10,000. And then if I need to, I can add in 100,000 or whatever. So I'll give you a moment to grab your calculator. So go ahead and hit pause and put this into your calculator and fill out the rest of the table and then come back. Okay, welcome back. So let's go ahead and see what we've got here. 10.24695. 100.024996, etc. What have we got here? 1,000.0025, and then 10,000.00025. Okay, so as my sequence of inputs approach positive infinity, my sequence of outputs also are growing larger, right? 10, 100, 1,000, with some fractional part, but still the idea is it grows to infinity. So that is our answer. The limit as x approaches infinity of the square root of x squared plus 5 is infinity. Okay, we're going to do a similar thing here with, we're taking a look at the limit of 2 over x as x approaches negative infinity. So what is that going to look like? So again, we're going to make our little table here, x, 2 over x, and this time we want as x approaches negative infinity. Again, the sequence itself doesn't matter. It's just that the characteristic is that it approaches negative infinity and fairly quickly, right? So basically, you're going to use the same numbers, just throw negatives in front of them. So go ahead, put that into your calculator, hit pause, and then come back and compare your results. Okay. So hopefully, unlike me, you remembered to change the function in your calculator to 2 over x. I forgot to change mine, so I had to go back and fix that. So always make sure you change your function when the function changes. But in any case, this makes sense, because if we're plugging in negative 10, this is negative 2 over 10. So that's negative 2/10, etc. But if you didn't see that, that's okay. In this very last one in my calculator, I got negative 2e to the negative 4. We did discuss this in a previous video, but let's go ahead and talk about what this is. This is negative 2 times 10 to the negative 4th. So this means I'm going to move my decimal place 4 places to the left. So here's negative 2 with the decimal here. 1, 2, 3, 4, and then backfill with zeros, and obviously move the negative out in front. So that's how I got that answer, negative 0.0002. Okay, so again, we take a look at as the sequence of inputs approaches negative infinity, what's happening to the sequence of outputs, right? They're getting, even if we don't pay attention too much to the negative signs, they're getting smaller and smaller, right? Negative 2/10, negative 2 100ths, negative 2 1,000ths, negative 2 10,000ths. So this is actually approaching 0. So the limit here is 0, which kind of makes sense, because if we take a look at a fraction is very small or close to 0 when the denominator is very large. Whether the denominator is very large in positive or very large in negative, it's still approaching 0, right? You can even, again, plot those on a number line and see the march toward 0 of the points on the number line. So let's try a couple here. and see how this goes. So I'm going to change one of these up just so that they're not all toward positive infinity. I forgot to add a negative in front of one of them. So let's do the last one as a negative infinity. So I'm going to add that negative in there. And you'll notice in all these, since we're only approaching in either infinity or negative infinity, you only have to do one table. You only have to check from one direction. Unlike with when you approached, like as x approached 2, you had to check both from the left and from the right. Well, with infinity, it's really this concept of growing out without bound. So you can only approach infinity from one direction. You can't approach infinity from two directions, right? So you only really need to do one table. So go ahead and for the first one, we're going to make I'm going to make a little table up here, start at the top, and we've got our 10, 100, 1,000, 10,000, and you're going to make sure we put this into our calculator as 3x divided by parentheses 2 minus 6x close parenthesis. Okay, so I'll wait for you. Go ahead and hit pause, check this out, and see what you get as an answer. Okay, so in doing my table for this first problem, our sequence of inputs approaches infinity, and our sequence of outputs approaches negative 0.5 or negative 1/2. Okay, so let's set up our table for the next one, or you can basically use the same table. You just have to change your function, right? So go ahead and do that. And again, 3x cubed divided by parenthesis x squared minus 4 close parenthesis. So go ahead, hit pause, change your function, and the table should automatically calculate for you, and go ahead and fill that in and come back. Okay, so with your calculator doing your tedious calculations for you, we used the limit as this approaches positive infinity, and we notice that in looking at the sequence of numbers that we're getting out here, these are growing without bound. So this is approaching infinity. So this limit is also infinity. So I want to take a quick second to compare these two problems. Why did one come up with a finite number, like negative 1/2, and the other come up with infinity? Well, if we take a look at each fraction here, and we pay attention to what's called the degree of each of the polynomials. So there's a polynomial in the numerator, a polynomial in the denominator. And this is, we compare the term with the highest degree, right? The degree implied here, the degree implied is a 1 on each of these, right? So notice the degrees are the same. And notice we take 3 divided by negative 6 is negative 1/2. Okay, so the degrees are the same. So this means as x grows, both the numerator and denominator are essentially growing at the same rate. So when x goes from 10 to 100, both the numerator and the denominator go by a factor of 10 and 10 to 100. And so really what matters then are the coefficients, right? So 3 divided by negative 6. Now let's take a look at the next one, and we take a look at the leading term, or the term with the highest exponent, and notice in this case the numerator has a higher degree 3, compared to degree 2. So now when their numerator and denominator are growing, when x is growing, we're cubing in the numerator and only squaring in the denominator. So every time we make a jump of from 10 to 100, we're actually going by 10 cubed versus 10 squared, right? And then from 100 cubed and 100 squared. So this is by a factor of 1 more, right? So the numerator is growing faster than the denominator is. And we can see that in the results in the table, right? So every time the numerator grows, it grows faster than the denominator does, and therefore the fraction overall gets larger and larger, and we see that represented in the output in the table. Okay. All right, so we've got one more, and we said we're going to change that to as x approaches negative infinity. And I want you to take a quick look at the degrees here. So we've got degree 1 over degree 2. So this actually doesn't match the previous two, right? The very first one was degrees are the same. Second one, the degree in the numerator was larger. Here, the degree in the denominator is larger. So maybe you might take an educated guess of what might happen here if we think about a fraction where the denominator gets large what might the limit of the outputs go to? Okay, so go ahead and set up your chart. Right, and this time we're going -10, -100, -1,000, -10,000. And go ahead, hit pause, check this out, see what happens, and report back. Okay, so compare your results to mine, and hopefully got the same thing. If not, double check that your function is correctly inputted into your calculator. That's 3x divided by x squared minus 4. Notice the change from the second problem. The second problem was 3x cubed over x squared minus 4. This is just plain 3x over x squared minus 4. And notice that as the sequence of inputs approach -infinity, the sequence of outputs are approaching 0. So the limit here is 0. So we have an example of each type of problem when we're dealing with infinity or -infinity, and that is when the degrees are the same. Their numerator and denominator are growing at the same rate. We take a look at the leading coefficients. When the numerator is larger degree than the denominator, the numerator is going to grow faster than the denominator. And when we're dealing with fractions where the numerator is larger, we end up with bigger numbers. And then in the last one, the denominator has the larger degree. And when you have a fraction where the denominator is larger, then you end up with a small fraction.